So before we get started on Raoult's law, I wanted to briefly review vapor pressure curves. And if you remember, if you take a liquid and you put it inside a container and you change the temperature, the vapor pressure, that is the gas that comes off of the liquid, increases in a fashion something like this. This would be the vapor pressure, right, and the temperature, and then it increases exponentially with temperature. So that's what it looks like when you have a pure substance. But what happens when you have a mixture? And Raoult said pretty simply, let's say you have the red molecules, right? Like this. Each of them have their own vapor pressure curve, like that. And then the blue molecules will have a vapor pressure curve. Let's say it looks like this. Right? It has a higher boiling point, so the vapor pressure is low for a long time, then rises. So that belongs to the blue ones. Well, if you wanted to know the vapor pressure of the mixture, all you need to know is the fraction of molecules of this type and the fraction of molecules of this type, and then calculate the total pressure as the sum of those two fractions. Now, when we do this in practice, what we do is we do the following. Let's say the blue molecules, right, they have a pure vapor pressure at a particular temperature. And so we're going to use a little knot here to indicate this is the pure substance. And the red ones will also have a pure vapor pressure. So we'll call that P for the red, right, like this. So that's for the pure substance. In the mixture, the way we calculate the contribution to the total pressure is by using the mole fraction that you learned in the gas laws chapter, but we can apply it to a solution. And so we're going to get the pressure that is of the red molecules in the mixture. Then what we do is we take the mole fraction of the red molecules times the pressure of the red molecules they would be exerting as a pure solution. And we do the same thing for the blue molecules. So the pressure for the blue molecules awesome. Well, that's blue, but it's the dark blue. Pressure of the blue is equal to the mole fraction of the blue times the pressure of the blue molecules when they're pure. And to get the total pressure, then we simply say P total. And this would be the vapor pressure above the liquid, right? So this would be vapor pressure above the solution. That would be equal to the partial pressure of the red plus the partial pressure of the blue. So that's how we find the vapor pressure above a solution, is we just take into account for each component of the liquid, right, of the solution, we take into account the pressure exerted by each one separately and simply add them together. Now this is what we do when we have what's called an ideal solution. In an ideal solution, the individual solvent molecules have the same intermolecular attractions with each other as they do themselves, so there's no energy change when the solution is formed. So in this particular solution, what we have is, for example, 1, 2, 3, 4, 5, 6 red molecules. In total, there are 18 molecules in this mixture. So the mole fraction for the blue would be 6 divided by 18, or a third. And then the mole fraction for the red would be equal to 12 over 18, or 2/3, 0.66. Okay. So in essence, you know the moles of each, right? You add them together and you divide each component by the total number of moles, and that gives you the mole fractions of each. So here we have a mixture of hydrocarbons. Now hydrocarbons, because they're all nonpolar, hydrocarbon mixtures behave as ideal solutions. So we have a solution that contains 0.75 moles of heptane and 0.36 moles of hexane at 347 Kelvin. Calculate the vapor pressure of the solution, and then some additional data is given. Right? These are the vapor pressures of the pure heptane and hexane, respectively. So to calculate the total pressure, we say P total, or the vapor pressure, right, for the solution will be the mole fraction of heptane times the pressure of pure heptane plus the mole fraction of hexane times the pressure of pure hexane, like that. So this value is 324.34, and then this value is the 837.74 millimeters of mercury. To calculate the mole fractions, let's say, for example, for the mole fraction of heptane, that would be the moles of heptane over the total, right? So that's 0.75 divided by 0.75 plus 0.36. There's moles on the top, there's moles at the bottom as units, and these moles will all cancel out. Well, that ends up ending up as 0.6757 moles. Mole fraction. So it's unitless. Now, you could calculate this, do the exact same calculation for hexane, or you could just know that since there's only two components, 1 minus the mole fraction of heptane can be also used, and that will give you 0.3243. So, this is for hexane, sorry. We can plug all the numbers in, and your P total, which is your vapor pressure above the solution, ends up being 490.8 millimeters of mercury. Okay, so that's how you calculate the vapor pressure for a pure or for a mixture of two hydrocarbons. So one of the handier things that you can do with binary mixtures is create what's called a vapor pressure curve. So in a vapor pressure curve, you actually only, for a binary mixture, that means a mixture that only has two substances in it, you only need to know two values to create the vapor pressure curve for all mixtures of the two substances. Okay, so let me show you how this is done. First of all, let's say we're doing heptane and hexane again, right? Well, when the hexane, heptane, when the heptane is 100% of the mixture, that's down here. So this can represent heptane. Heptane has this vapor pressure when it's a pure substance. So this would represent, from our previous graph, or data, right, at that particular temperature, 324.34. So I'm just going to say 324. And these units will be in millimeters of mercury since we're using that for our data. Now, that's when you have pure heptane, 100% heptane. Now, when you have 100% hexane, what that means is you have 0% heptane because it's a binary mixture. You're over here. So then this represents the vapor pressure of pure hexane. For that particular problem, 837.4, right? 837.74, so we'll call that 837.7. Now, these individual lines represent the vapor pressures of each of the solvent solution components, right, as a function of their mole fraction. In other words, this line, right, represents, the contributions of each one of these parts of the equation at the different mole fractions. So let's say you had a 60% heptane mixture right? The heptane pressure would be this value. The hexane pressure would be this value. And if you add them together, it actually gives you this line up here. So what we do when we do a vapor pressure curve is we plot the two vapor pressures of the two components of the mixture as a function of the mole fraction, basically graphing from 0 to 1, and then we just connect the points. And so this line represents the vapor pressure of the solution. So the very handy thing, if you have lots of different mixtures and you need to know their vapor pressures, then you can just graph this kind of your data like this, and then you don't have to do all the individual calculations. The only drawback is this kind of calculation only applies to one temperature, because if you remember what we were talking about for the vapor pressure curves, they're very dependent on temperature. So you have to know what these values are at each temperature in order to create this graph at each temperature. Another important application of Raoults law is when you have a non-volatile solute. So what does non-volatile mean? It simply means it won't vaporize. So when you're looking at a mixture of two substances, then you realize that the pressure total is going to be equal to the pressure of the non-volatile solute, right, times its mole fraction, plus the pressure of the solvent times its mole fraction. And well, this term is 0, so it goes away. So in order to calculate the vapor pressure above a solution containing a non-volatile solute, you just need the mole fraction of the pure substance in order to calculate its vapor pressure. So we have a question: calculate the vapor pressure of water in a solution containing 0.2 mole fraction of glucose. The water's vapor pressure is 17.5 torr at this temperature, which was room temperature. Okay, so what we do is simply do this. The pressure of H2O is going to be 0.8, because 20%, 0.2 is glucose, so 0.8 is the mole fraction for the water, times 17.5 torr, or millimeters of mercury if you're more comfortable with that, and that ends up being 14.0, or 14, rounding, sorry, torr. So it's fairly simple to calculate. Again, these are given as mole fractions. If you're given masses, you have to convert those into moles and then calculate the mole fractions. If you're interested in what the vapor pressure curve looks like, right, it's pretty simple. This is H2O. This is the mole fraction of water at the bottom. I have at 1 mole fraction of 1, I have 17.75 torr, or 17.5 torr for water, and then it's just a straight line to 0, well, fairly straight line to 0. And then at 80%, if you were using a graph, then you would simply go to this point here, and that would be your vapor pressure for water at a mole fraction of 0.8. So the next two cases that we'll be looking at are non-ideal behaviors. And what I want you to remember is the type of intermolecular attraction and how that affects the vapor pressure. Okay, if you don't remember all the details of the vapor pressure curves, you'll be okay. So what happens when two molecules that are mixed are more strongly attracted to each other than they are to themselves? So the intermolecular forces of attraction between two molecules is stronger than in the pure states. Okay. Well, when you start making mixtures of these substances, what ends up happening is the vapor pressures begin to drop for each of the components. So instead of being a straight line, in the mixture, they're happier being mixed. The result is, rather than following the line for ideal behavior, there's a significant negative deviation, that it's less than, right? A negative deviation from the ideal behavior. So this is vapor pressure curves, right, for substances that are more stable in solution than they are by themselves. Now, the opposite can also be true. That is, you can have solutes and solvents that are less stable together than when they're pure. And so when you mix these things together, as soon as you put them into the solution, the vapor pressures of the components increases because there's less to keep them in solution. They're less stable mixed, right? As a result, you get a positive deviation in the vapor pressure curve, and you get more volatile, more vaporization taking place as a result of the instability of the solution. So those are the four types. Typically, we don't do the solid one yet, but it fits in with this information so well, I just put it in there. You have the ideal behavior where intermolecular forces are unaffected by mixing. That is, they're the same before they're mixed and the same in solution. And then we have the solid that's non-volatile. And when you have a solid in a solution that's non-volatile, it affects the vapor pressure by lowering it. Okay, and then the next two are solutions that are more stable than their solvents, which decreases the vapor pressure, and then solutions that are less stable than their individual solvents, and that increases the vapor pressure. So those are the four kinds of effects that we're looking at.